My name's David Wilmoth. I'm with Harvard University. This is the Harvard Halogens Flight Instrument. This instrument measures CLO, which is chlorine monoxide, BRO, bromine monoxide, as well as chlorine nitrate. Those three inorganic halogen molecules, which are prevalent in the stratosphere, actually present in very small concentrations, but potentially impactful for ozone chemistry. So ozone is a gas that's primarily present in the stratosphere. It protects all life on Earth and from harmful ultraviolet radiation from the sun. And so chlorine and bromine are well known to destroy ozone. So one of the reasons we're interested in measuring chlorine and bromine is we want to make sure that we understand the chemistry so that we understand ozone. And so every year there's these seasonal ozone holes at the poles, which I think everyone is familiar with. But chlorine and bromine are everywhere in the stratosphere, and so we're measuring it over the mid-latitudes this summer as part of the DCOTS campaign. And one of the things we're interested in is this process of convection that brings air up from the troposphere into the stratosphere. It bypasses the sort of normal way the atmospheric circulation works. And so if we're bringing tropospheric gases into the stratosphere, does that potentially have an impact on the halogen chemistry? And also with the water vapor that we know for sure comes up with these convective processes, is it possible that the chemistry of the stratosphere is impacted that way as well through heterogeneous reactions? So that in a nutshell is the reason why we're interested in halogens. So specifically, most of the halogens that make it to the stratosphere come up in the organic form, which means they have carbon in them, but then it's converted into inorganic chlorine once it's in the stratosphere. And so the three major forms of inorganic chlorine in the stratosphere are HCl, hydrochloric acid, chlorine nitrate, and CLO. So we're measuring two of those three. And we also have a way to figure out the total amount of inorganic chlorine so we could actually calculate the HCl, the one we're not measuring. So we do have a pretty complete picture of what's happening with the chlorine chemistry over the US in the summer as part of this mission. That's one of the goals. And also for bromine chemistry, BRO, the molecule that we measure, is the most significant inorganic bromine molecule as well. So again, these compounds that we're measuring are present at very small concentrations, so parts per trillion units, which is very, very small. But because of the way the catalytic reactions work, that a single chlorine or bromine could destroy many, many thousands of zones. So it's that's the reason why we care, even though they're present in very small concentrations. So if we go back in time to think about what things were like in the mid-80s, there was everyone was using CFCs, chlorofluorocarbons, and all sorts of deodorants and sprays and refrigerants, and people realized that that was actually leading to ozone destruction. So those things began to be phased out as part of the Montreal Protocol, which is this international agreement. It's the most successful international agreement in history. All nations on Earth have now agreed to limit their use of chlorofluorocarbons and also halons, which contain bromine. And so as part of that, slowly over time, we are seeing the amount of chlorine in the stratosphere go down, and we'll continue to see that over time. But one of the other things we're able to do in this mission is to actually take a look with this in situ payload. So in situ means we're actually measuring right in place as we're flying through. So we have satellite measurements of these, but satellites are limited in terms of how detailed and specific they can actually determine the concentration. So we're able to look very carefully at what the chlorine, inorganic chlorine concentrations are in the stratosphere right now with a precision that's not possible from a satellite instrument. And this is the first time this has been done in quite some time, so it's very helpful to do that. Okay, so this instrument is called the Harvard Halogen Flight Instrument. The way we detect CLO, I'll just use that as an example, first of all, is we add NO, which is nitric oxide, to the flow of air as it's going through the instrument. So the nitric oxide reacts with CLO and very rapidly converts it into chlorine atoms. And so we actually detect those chlorine atoms by a process called atomic resonance fluorescence. So there's a vacuum ultraviolet light source that we actually make ourselves that excites the chlorine atoms in our flow ducts, and then those fluoresce. So they emit light as the excited chlorine atom relaxes back to the ground state, and we detect that light with a PMT. And so by titrating with NO, we can determine how much CLO is there. For chlorine nitrate, which is a larger molecule, we heat it up very hot, 220, 230 degrees Celsius. We break the CLO NO2 bonds, and so with that CLO fragment of the chlorine nitrate, we titrate that with NO, and by the same process as the ambient CLO, we convert that to chlorine atoms, and we detect those chlorine atoms. So basically, by modulating temperature and the amount of nitric oxide we're adding, and detecting chlorine atoms, we can determine the amount of CLO and chlorine nitrate in the stratosphere. So this instrument flies in a very large, it's called a superpod. It's a big cylinder that sits underneath the left wing of the plane. The air, so the plane flies along, and the air, as the plane's flying along, goes right through our instrument, up and out, and we have about 10 milliseconds to make this detection as the instrument's going along. And so that's how we do it. And so for bromine, similar process. For BRO, we also titrate with nitric oxide and detect the bromine atoms. It's a similar atomic resonance fluorescence technique. The difference is we have a different light source that's tailored for bromine, and we change some purge lines. But other than that, it's a very similar detection technique. So this instrument has 4 different detectors, and depending on how we set it up with our light sources and the heat, we could measure, again, CLO, BRO, chlorine nitrate. When we have flown this instrument over the polar vortices, there's another molecule called CLO dimer, or chlorine peroxide, that's present in very high concentrations. It's unique to the poles, so we only measure it there. Because it's only present then when it's very cold and very dark. But this instrument can also measure that as well. And so that's essentially how we do it. It's these, if you want to catch it in the shot, these are the 4 different detectors. There's a custom vacuum ultraviolet light source inside of each of these housings, along with quite a bit of custom electronics. The detectors are here at a right angle. These are called PMTs, photomultiplier tubes. That's what actually does the detection. This here is the dissociation heater. This is a custom part that one might think that having a heater that could heat to 220 degrees Celsius isn't that difficult. And it's actually not to heat it. The challenge is making a heater that's inert. Because if you have any sort of metal surface or anything that you might normally think of with a heater, it's going to destroy the chlorine atoms and impact the measurement. So this is a custom design. You can't see the inside. There's a grid of 28 strips of silicon wafers that we're using to resistively heat up. And because silicon is inert to chlorine, but we've plated the ends of the heater with titanium, nickel, and gold to get the electrical conductivity, and it works quite well. And these are the inlets in the front, so it's a double ducted system, so the air's going through and measuring simultaneously in each of the 2 ducts. And again, with the 4 detection axes, we have a lot of flexibility in terms of whether we could measure CLO in 4 places if we chose to, or we can mix it up depending on the heater and which lamps we put in. Sometimes people see the instrument and their first reaction is, well, what's all this yellow stuff? Okay, that's Kapton tape. So underneath this tape is insulation. It's called Nomex insulation. It's actually primarily used in fire suits, but it's very good for flight use. It provides some thermal insulation and so the Kapton tape's just a protective barrier over top of that. Most of the real intricacy of the instrument you can't see just by looking at the outside. There's quite a bit of custom electronics inside the gas deck and this deheater control box and the different housings. In the back is a data system that we built that can process all the data in real time, and we're actually able to send the data down from the plane in real time. So as the plane's flying along, we get an updated measurement. So we don't have to wait for the plane to land to find out how much CLO or chlorine nitrate or BRO we're actually measuring.
Now, with people using less and less, or putting less, how is it getting into the atmosphere now? How's chlorine getting up there now?
So the primary source of the chlorine that's up there now is the same source of the chlorine that was up there before. So the CFCs have very long atmospheric lifetimes, some of them over 100 years. And so it'll be a long time before we can undo the effects of putting all those CFCs up there all those years. But there's some natural source of chlorine. There's still anthropogenic chlorine released, but the primary source is still the CFCs that were put up there a long time ago. For bromine, there are halons, the anthropogenic sources that people put up, but there's also a significant natural source of bromine as well. So we're never going to have a stratosphere that's free of chlorine and bromine, but the way that unintentionally the human population distorted that balance to put so much additional chlorine and bromine into the stratosphere, that's going to take a while to undo. But we're on the right track. We're on the process of recovery. It will take many decades more to get there, but we are progressing in the right direction. The important thing was that we took action when we did. There's been some studies that have come out that have looked at what's called the world avoided. So what would happen if we didn't have the Montreal Protocol, if we just continued with business as usual from the late 80s till now? And it's a very grim picture that there would be quite a bit less ozone, quite a bit more UV radiation reaching the Earth. We'd all be getting more skin cancers and crop damage and all those negative effects of too much UV. Not to mention that CFCs are greenhouse gases, so it would be bad for climate change too. So we made as a global community, it was a great decision to move forward with that, and hopefully we can see similar things with climate change. There seems to be a little more resistance to that, but hopefully we can get there.